Hey students, we are looking at different types of circular motion in this video. The first is going to be flat car turns, so when a car is turning on a nice flat road. And also we're going to start looking at things moving in vertical circles, all right, not just the horizontal variety. So part A of our notes, flat car turns. So we're not talking about a banked road. We'll actually get into that later. That will be our example of or our use of inclined planes. I have this quick picture here. This car is moving. If you think of this segment of our circle, it's moving clockwise. That's why I have this arrow right here. Okay? Whether it's moving in an actual circular track or if it's just making a turn, we can approximate that turn as being like a piece of the circle. So I have R here labeled as the radius of that segment that's acting, or that's a fraction of a circle. Here's a top-down view, and here's a view kind of from the side, from the rear. This view is like if you were standing right at this spot, you were watching the car leave you behind. It's going to be helpful to look at both views. So we're going to start just by drawing a free body diagram, kind of typical. I'm going to do one for this top view and one for this side view. So top view. Well, I always start with a dot. All right, if this is a bird's eye view, there's definitely normal force and weight, but those would like be coming out of the screen and going into the screen. Okay, from this top-down perspective, what forces are acting towards the center of the circle or away? And this is where it gets a little tricky. With the ball on the string, we knew there had to be a centripetal force, and it was easy. It was coming from the string. This car is turning. Okay, it's moving with some tangential velocity, and it's making a turn. Based on what we said last time, there must be a force acting towards the center of our circle. There has to be. Well, what force do you think that is for a car making a turn? It turns out it's a frictional force between the tires and the roadway. So in my top view, I have this frictional force to the right. So here, let's look at this side view. I told you this side view would come in handy. Free body diagram. Well, here I can clearly see, okay, there's a normal force. There's going to be mg. This car is making a turn. It's not as obvious in this perspective. There's a frictional force between the tires and the roadway. And this isn't friction in the same sense of the wheel gripping the road to make the car move forward. That's actually a different type of friction. We'll get into that when we do rotation. But if a car is turning, there must be this gripping force that's preventing the car from sliding out. It's almost best to understand this by thinking what happens if there isn't friction. If you've ever seen like a video on the news or online where cars are sliding out, maybe the road is icy or it's slick, but if a car slides out, it is not able to turn and it keeps on going straight because there isn't that sideways friction. If this car is able to follow this curve, those tires must be able to grip sideways. And that gripping frictional force is what's able to pull it, keep tugging it toward the center of the circle. So I have a friction like this. There is friction on each of the tires, but for my free body diagram, I'll just simplify it like this for right now. Okay? Well, key piece of information. All right, what I just said. This sideways frictional force is what's keeping the car moving in a circle. I'd write that down. Okay, that's explaining what's happening. Okay, that is the force acting towards the center. So I have the same diagram, I just kind of made it small. We got to figure out what type of frictional force, because remember there's two types. There's static friction, there's kinetic friction. We don't want the car sliding toward the center. That'd be weird. And we certainly don't want the car sliding away from the center, because that's when a car is sliding out. It's not able to navigate that turn. So if you think of the car moving left or right towards the center or away from the center, we don't want it to move that way, which means it must be a static frictional force. Okay, well, for again that side view, just because it's a little easier to recognize, now I can put an F sub S, the sum of the forces in the centripetal. Well, there's only one force towards the center of the circle, that's static friction. That's equal to MAC, that equals to mv squared over r. If you forgot, static friction is mu times the normal force. And in this case, since our turn is flat, the normal force is equal to mg. You could prove that real quick if you wanted to. The sum of the forces in the y direction. This is all stuff we used to do. N minus mg equals may. That equals 0. So the normal force equals mg. That's what I plugged in. Oh my goodness, right there. So that equals mv squared over r. All right, so there's a basic setup for this car that's moving around in a circle. Okay, another key idea. This equation that we just wrote down is a very important equation. Okay, at first it's just, yeah, that's a basic equation for Newton's second law, but this is actually setting the parameter, what is required for a car to make a turn. In order for a car to be moving in a circle, there must be this centripetal net force. Well, for a certain curvature, how tight that circle is r, moving at a certain speed, v, you must have enough static friction. If you don't have enough static friction, if this number is too small, well, then this number won't match the required centripetal force. And if you don't have the necessary centripetal force, the car won't be able to go in a circle. This is telling you how and when a car is able to navigate. You have to have a certain amount of friction, so you have to have a certain grippiness of tires. Your car has to have a maybe certain weight. And then obviously if you're going really fast around a turn, you need this to be a larger value. You need more friction. If you're doing a really tight turn, maybe you've been in a car and someone just cranks the wheel to the right, makes a super sharp turn. Okay, you could imagine there must be a lot of centripetal force. You have to have grippy enough tires. Okay, that's why when roads are icy or if you're going too fast, there's a high likelihood of your car slipping out. The reason your car slips out is because you don't have enough friction. This is kind of the requirement. To make that turn, you need to have the frictional force matching that mv squared over r at maximum, or at least at minimum. Okay, we'll talk about this more later. So those are our cars making these flat turns. It's still just setting up Newton's second law. Okay. Part B, looking at vertical circle. So now I have my ball at the end of the string. Okay, here's the center of my circle, but instead of swinging it horizontally, I'm swinging it around vertically. And really what I want to do is set up Newton's second law at 3 different spots and just compare, because things are going to be a little different now. We're not always going to have the exact same equation, and here's what I mean. At position 1, let's draw a free body diagram. At position 1, this ball, this is the ball we're looking at, the object, it obviously has some weight, mg. There's also this tugging tension force, so there's also T. Well, the sum of the forces in the centripetal, remember that means towards the center or away from the center. If I say towards the center is positive, tension is acting towards the center, but the weight is acting away from the center. That has to add up to mv squared over r. Okay, let's look at position 2. At 2. My free body diagram. Well, when the ball's right here, the string is looking like this. Now I have tension going to the left. I still have weight acting straight down. Weight is always straight down. The sum of the forces in the centripetal. Notice the weight is no longer in the centripetal direction. It's no longer toward the center or away. Tension still is. and that tension force is still acting towards the center. It should still be positive. Hey, our sum of the forces has changed based on the position. At spot 3, let me go to a green pen when the ball's right here. At 3, free body diagram time. I still have the weight. What direction is tension? It's acting downward. So it's a little tough. I'm sorry, I can't draw very well. Tension should also be on that free body diagram, both acting downward. And so the sum of the forces in the centripetal, well, both tension and mg are pointing down toward the center. So I add them up. T plus mg equals mv squared over r. Again, I have things plus or minus, not because they're up or down. That's what we used to do. It's positive if it's towards the center. It's negative if it is away from the center. And so for the circles, and if you do 4, you could. It's going to look very similar to number 2. Okay, for number 4, let's see, what color haven't I used? Can I do like white? Aha, ball's right here. Again, I only have the tension acting this way. You're going to get an equation that's very similar. Okay, but for vertical circles, the forces that are acting in the centripetal direction, they're changing. Okay, sometimes it's just tension, like number 2 and number 4. Sometimes it's tension and the weight. Sometimes the weight is acting in the opposite direction of the centripetal force. Sometimes it's helping. Sometimes it's toward that direction. Okay, but how you figure that out? Nothing to memorize. Just set up your sums of the forces. Draw those free body diagrams. Okay, I actually want to focus in on that part 3, that position 3 up here. I'm going to redraw number 3. Okay, there's that free body diagram again. Here's that sum of the forces. All right, this equation is really important, and it has to do with this bullet point that I have right here. If I want something to be moving in a vertical circle, when I'm swinging something around, I should feel that tug, that tension in the string, right? It's that tension that keeps tugging it. Well, I could slow down, and by slowing down V, I would lessen the tension force. If I swung that ball way too slow, okay, I did it a little too slow, the ball would like go like this, and then if I'm not swinging it fast enough, it would die, and it would stop swinging in a circle. Okay, if I am not swinging with sufficient speed, it's not going to continue that path. I need to swing with enough speed so there's still at least a little bit of tug from that tension force. The minimum speed based on this equation is right as t goes to 0. As long as there's some itty-bitty tug, I'll have this continued circular path. But right when there's no more tension in the string, there's no more thing right when the ball gets here. There's nothing that's going to keep pulling it towards the center, keep this circular path. It's going to do this dying trajectory that I've drawn. So at bare minimum, or kind of when the object ceases to move in a circle, is right as t approaches 0. And you could possibly solve, and we'll see examples of this, solving for v at that minimum amount. Okay. Vertical circles can be a little tricky because look at this equation, okay, or go back here. If I'm going to have tension constant, if I want to swing the ball with a constant tension, the speed of the ball is going to change. Or if I have the ball swinging and the speed is staying the same, there will be different tensions at different points. All because tension and different forces are going to contribute to that centripetal force as the ball is moving in its path. Okay, there's only one slide left I want to show you. It's building off of this thing right here. I have here a roller coaster. So now instead of a ball moving in a circle, I have like a roller coaster cart. But it's at position 3 again. All right? Instead of it being like a ball at the end of a string, it's the normal force applying a force towards the center. And this is another example of how you need some bare minimum speed. The sum of the forces here is the same. Sum of the forces, that should be in the centripetal direction. So you make a mistake myself all the time. Look at that free body diagram right here. I have Fg, the weight, plus the tension equals mv squared over r. Imagine a roller coaster. You have to have some bare minimum speed, otherwise the car is going to get to the top and you're going to plummet to your death. Okay? That shouldn't be a tension, my goodness. That should be the normal force, N for normal force. So you need to be moving fast enough so there's still some normal force, and that minimum speed is right as that normal force goes to zero. Okay, if the normal force gets to zero right here, well, then it's no longer touching the track. That's when you get that dying trajectory. Okay, it's often easier to see this in practice, which is what we'll do in the near future. Okay, anyway, thanks for watching these two examples on circular motion.